Hello friends of Wakefield Accelerators and Fluid Dynamics. Welcome to my channel. In this video I will explain to you how to design and run a fluid dynamic simulation of a multi-slit nozzle, also known as Lord of the Chimneys. So if you watched my previous video where I explained to you how to design a slit nozzle and the advantages of using such a nozzle, I mentioned there that the length of this nozzle cannot, it can be made as long as you want, but there is a huge disadvantage because as you increase the length, you also need to increase the height. So it's not practical to design a nozzle from one piece with very long lengths. And as alternative, I will show you here how to solve this problem. So basically, you just need to stack all those slit nozzles, or like you see here in the figure. And here is the model that you'll use in the simulation. So you remember, I hope you remember that you need to model only the fluid part. You don't need to model the real walls. For instance, here is the model made for manufacturing with walls and everything. So of course you don't need all these parts. You just need the internal part. And here is an example with 3 nozzles, but you can stack as many as you want. So for instance, here I stacked 10 slit nozzles, and I put on each nozzle a different pressure, an increasing pressure, and here is the density profile. Of course, this is an extreme case, but who knows, maybe you might need such a density profile. Using this kind of profile this kind of nozzle has a huge advantage because you can put any combination of inlet pressures here, or you can use any kind of gases. So of course this will give you a very versatile gas target. Now if you look here in the figure, you'll see that the nozzles are slightly overlapped. So the reason for this is because if you don't overlap properly, you will end up with such a density profile where the density profile shows a sudden decrease in density, especially close to the exit of the nozzle. And this might have an important effect on the quality of the electron beam. Here is an example where an example of a density profile generated by 3 nozzles overlapped about 6 millimeters. So I can't remember how much was here, but it was I think 4 millimeters overlap. So 4 plus 4 from each side. So 4 from here and 4 from here. So in total 8, if you want to take it like this. And you see the density profile is much smoother, and so this is 1 millimeter above the nozzle, 2 millimeters, 3, 4. So you see is much smoother density profile. Alright, so let's get started with the simulation. The steps are like before. It's easier to just use a previous case, so let's take the chimney nozzle, simple. And right click and duplicate. Okay, this is the nozzle. I'll move it here. I will give it a name. Okay, and we don't need So we need to make sure that the previous settings are reset, so that we will not have some issues while we trying to mesh or import the geometry in ANSYS Fluent. So right click and reset, and the same on ANSYS Fluent program. Okay, so you see here there is nothing. Okay, let's open the geometry and right click, edit geometry in design modeler. I'm using the design modeler, but feel free to use whatever program you want. Space Claim is the one that is by default here in ANSYS Workbench, or whatever CAD program you want to use. Okay, so if you remember, this is the chimney nozzle. So what we have to do is duplicate this, actually triplicate this this nozzle. So what we will do is very simple. Solid, and we go to create pattern, and the geometry of course is this one, and direction, we can go in this direction or this direction, it doesn't really matter. You can go so let's see, not like this, like this. So this is in the positive direction. It's a good idea to put it in the positive direction. Apply, and here is the important thing: how much you want to where do you want to have the nozzles, and how much they should be overlapped. So for that you will need to know the distance from the outlet length. I can't remember how much was here, so I just go to plane 4, which is here, and okay, it wants to generate. So you see now, if you put too much, it's moved a lot in that direction. So here is 10 by 10, so 20 centimeters. So it's clear that we moved this, we created too far away, the second slit nozzle. So edit selections, the geometry we don't change, and this one, if we put 20 and generate, now you can see it's exactly, oops, I want to rotate. So there is no overlap between the nozzles, they are going exactly like this. Now if you want to see it better, okay, okay, so I made a mistake here. I didn't want to extrude that one, so this is the nozzle, and if I go here, box, right click and suppress, you can see now the nozzle properly, the exit. So you see there is no overlap, but we want to overlap it slightly. So let's go back, unsuppress, okay. And if you want to overlap, we just change here in pattern. We can put, let's say 18. So 2 and 2. It will be in total 4 millimeter overlap. Generate, so you see here is overlapped. But let's say we want 3 nozzles. So we put there 3, generate, and we have, so 2 plus 3 plus 1. So this will generate 3. So you see automatically also the outlet part is generated, which is a really great thing, and these are the nozzles. So we have inlet 1, inlet 2, inlet 3, and the one big outlet or pressure outlet. Alright, so let's say we are happy with this geometry. We don't have to do anything else. We have one solid geometry, that's all. We close the program, Control S to save it, and let's open the mesh, the meshing program. Alright, now insert. Let's try first to mesh it with multi-zone. I'm not sure if it works, but let's try. Okay, and method, the geometry is only one, and method multi-zone. Okay, I will keep the element size by default. Let's see what is doing. Generate. Yeah, it seems to be working. So, but the number of cells is too small, of course. So now we change the cell size or the element one of the sides. 0, 0, 5. Okay. Update. And let's see the status of the meshing. If you click here, you can see here how it's going. Okay, 137. For now I will keep it like this, but always remember to have many cells. So for my experience, for this geometry you'll need a few millions of cells to get an accurate solution. But for now we can keep it like this. Just this is just an example, so it doesn't really matter how many cells we'll have. Alrighty, and now it's time to give it a name for each boundary, and we will just define the inlets and the outlet. The rest by default it will be named wall by the program. So let's click on the surface, click here, right click, create name selection. So pressure inlet 1. Okay. Okay, the second one, so pressure inlet 2, oops, inlet 2, okay, and this one, pressure inlet 3. Now, if you don't intend to put different pressures on each inlet, you can select all three of them and give it a unique name. So you can edit all of them at the same time. I mean, you can define the properties of these boundaries at the same time. So the same pressure, for instance. If you want to put different pressures or different gases, then you need to give them unique name. All right, so let's select now the other surfaces. Okay. And here. this one. Okay. And here, this one and this one, right click and pressure outlet. Okay. Let's check. Pressure inlet pointing there, pressure inlet and pressure outlet, all six faces, sorry. Okay, so it looks okay, perfect. Now let's press update because we named these boundaries and we need to update it. That's it. Let's close the meshing program, Control S to save it, and let's go to ANSYS Fluent, double precision 62. In my case, you are limited to 4 if you are using ANSYS Student, which is the free version of the program. And also 1 million cells is limited ANSYS Student. For most of your simulations it will be enough, so you don't really have to worry about having just 1 million cells. Anyway, your computer will take a very long time to run the simulation if it's not on a high power computer or a cluster. Okay, we don't have to do anything else. Start. And now the geometry, the mesh is imported by ANSYS Fluent. Okay, inlet is marked properly, outlet is marked properly. Change the scale to millimeters for better visualization, and and plotting. Close, check. This will check just the mesh if there are any errors. No error. Report quality again is okay. Units, if you want to change density in instead of kilograms per cubic meter, you can change it to whatever units you want. You can do it from here. Just press new and you put a factor. I usually use in atoms per cubic centimeter because that is more relevant for Wakefield acceleration experiments. So you can do it from here. Alrighty. Now we choose the solver density based. Always will run a steady case, so it's not in time, but the simulation will run artificially. It will artificially give time steps so that it will reach the steady state regime. Maybe later I will do some transient examples, but not now. Energy equation, and here viscous by default is selected when you choose density based. This is the most appropriate model for this type of simulation, so compressible supersonic flows. I don't change anything here. By default I leave everything as it is. Okay, and I finished here. Now let's import the material. Double click on material, create edit, and now let's import helium. In experiments I use hydrogen and helium, very rarely other gases, so that's why I import helium. You can import any gas you want. Okay, copy, close. All right, and close. And now let's go double click on helium, and instead of density constant we will choose ideal gas. here are the real properties of the gas, so it's not not everything is defined as ideal, so don't worry about this. Change, create, close. Alright, double click on cell zone conditions, operating conditions 0, that means the gas target is surrounded by vacuum, so that's your reference. Alright, double click on fluid, change from air to helium. Sometimes people they forget to do this step, and by default the material taken in the simulation is air, so of course you'll have bad results. So don't forget to change to helium, apply, close. Okay, now boundary conditions, we have 3 inlets, and we can define so one bar or 100,000 and initial 99,000. It doesn't matter, this one just to be slightly less than this one to initialize the flow. Here I keep 5% by default. I put here a number, it doesn't really matter for this example. Read the manual how to define that thing. Now if I want 200,000 and 1, okay, again and again, close. And the last one, let's say 3 bar. So okay, now outlet, pressure outlet, you can put first with real vacuum level. If the simulation doesn't work, just watch the video that I made about divergence in your simulation and how to correct it. You'll put here a very close value to atmospheric pressure, so let's say 50,000 or something like this, or even 100,000. And you run the simulation until it's stable, then you can change back to gauge pressure, to the vacuum pressure, and run the simulation until you get convergence. Alright, let's change this one, and whatever number is there, close. Alright, now at methods, we keep by default second order upwind, which is very accurate for what we need. Solution controls, we don't change anything here unless we really want or we really need. Okay, residuals, I prefer 10 to minus 5. If you like 10 to minus 3, feel free to leave it. I put 10 to minus 5 even if the simulation doesn't reach this value. It's just to make sure that the simulation will keep running if the other parameters are still changing. So I didn't reach steady state regime. Okay. Now I like to monitor the density at the outlet. It's my way to run the simulations. You can monitor anything else. It doesn't matter as time as you monitor one of the parameters, so that it doesn't change anymore in time. Okay, pressure outlet, add here. Okay, now we don't need both of them, we can delete one. Okay, now we initialize. Okay, this is initialized, everything is fine. And now we need to go to calculation activities, autosave if you want. It's recommended to autosave just in case you want to go back to rerun the simulation if something goes wrong. You don't want to lose precious computing time, so you can go back a few thousands of iterations, load the data saved at that time, modify whatever you think is necessary to stabilize the simulation, and run again the simulation. It can save you a lot of time. Okay, also here probably you should know it by now. You can retain only some of the files if you want only the last 5 or all of them. It's up to you. Okay, run calculation, number of iterations. I put here a very big number. I can stop it anytime and resume the simulation, so I don't really care about an exact number here of iterations. Press check case in case you forgot something, no problem. And what we can do now, calculate. And now the simulation starts running. You watch the residuals, you watch the density at the outlet. I prefer the outlet because when the solution doesn't change anymore, I'm pretty sure that everywhere in the domain the solution doesn't change anymore. So I reach the steady state, the solution is theoretically converged. Now remember, the criteria for convergence is not only the residuals, that they should reach a very small value and shouldn't change anymore, but also the density at the outlet, for instance, shouldn't change anymore, and the mass flow rate the difference between mass flow rate between inlet and outlet should be less than 1% or as small as possible. So to check mass flow rate, go to reports, setup, and you choose all the inlets, you choose the outlet, and you have here mass flow rate, compute, and this should be, so when you compare the inlet with the outlet, this difference should be less than 1%. Okay, so that's pretty much it. I don't think I have more to explain to you. This is how to simulate an Lord of the Chimneys nozzle. If you work in the field, you will see very fast the advantages of using this kind of gas target. It's very versatile, so you can generate very complex density profiles. Thank you for watching, and if you like the video, subscribe, and if you have the means, you can support future video releases. See down below in the description how to do it. Thank you for watching. Bye bye.